In this chapter, we're going to study heat energy and heat calculations. The first law of thermodynamics tells us that energy in the universe is constant. It can be converted from one form to another, but energy cannot be created or destroyed. This temperature is a measure of the average kinetic energy of the particles. It's a measure of the average motion of those particles. Taking a piece of metal, putting it into the burner flame, increasing the heat energy, and then dropping it into water will show you that heat flows only from high to low. Delta H means change in heat, and that heat will have either a positive or negative sign. Not a positive or negative number, but a directional sign. A negative delta H means heat flows out. A positive delta H means heat flows in to the system. Your energy measurement then must have three parts: a unit, joules or calories or kilojoules, a number or value, and a sign to tell the direction of that energy flow. Negative exothermic, positive endothermic. Your specific heat capacity is the property that all substances have, and this is the amount of heat energy required to raise the temperature of 1 gram of a substance by 1 degree Celsius. Substances have many different specific heat capacities based on their structure. Some specific heat capacities listed here. You can see that liquid water has an incredibly high specific heat capacity. This is due to the hydrogen bondings in the liquid state between the water molecules, and it takes 4.184 joules of heat energy to change 1 gram of water by 1 degree Celsius. You can see as you get down to metals, they have very low specific heat capacities. This is why they're good conductors. It doesn't take much heat to change their temperature. You need to memorize the specific heat capacity of water. We will usually use the 4.184 joules per gram degree Celsius, occasionally 1 calorie per gram degree Celsius. The conversion factor is that 1 calorie is equivalent to 4.184 joules. To calculate heat then, you have to have the mass of your substance, its specific heat capacity, and the change in temperature that it undergoes. Heat calculations are pretty straightforward. How much energy does a copper sample absorb as heat? If its specific heat is 0.384 joules per gram degree Celsius, its mass is 8 grams and it's heated from 10 to 40 degrees Celsius. To solve a problem like this, you use the equation delta H is equal to mc delta T. Delta H is what you're solving for. This is the heat. M is the mass, C is the specific heat capacity, and delta T is the change in temperature. So taking that equation and plugging your numbers in for the variables, putting your units in, you get a delta H of 92.16 joules. Find the specific heat of a material if an 8 gram sample absorbs 60 joules when it's heated from 20 to 50 degrees Celsius. Again, you've got your delta H is equal to mc delta T. This time you're going to solve for specific heat. Specific heat is equal to delta H divided by m times delta T. Plugging your variables in and solving. Your specific heat is 0.25 joules per gram degree Celsius. Don't confuse the variables heat, delta H, and specific heat, C. Water has a specific heat of 4.184 joules per gram degree Celsius. If you have 35 grams of water at 98.8 degrees Celsius and it loses 4.94 kilojoules of heat, what's the final temperature? This problem takes a few more steps. First, you're going to solve for the delta T. To find the final temperature, since the water starts out at 98.8 degrees, and it's going to lose energy, its temperature is going to drop. So we first need to find the change in temperature. So delta T is delta H divided by MC. Plugging in, you need to convert your 4.94 kilojoules into joules so that your units will agree. Solving for delta T, since your water lost energy, its temperature dropped, so you would subtract that delta T from your initial to get your final temperature of 65.07 degrees Celsius. This is the final temperature after the water loses the 4,940 joules of heat. Another way to solve for heat is to use a thermochemical equation. In this method, you will be given an equation and a heat value associated with that particular reaction. Here you can see you've got C5H12, 8 moles of oxygen yielding 5 moles of carbon dioxide, 6 moles of water, and 3,523 kilojoules of heat energy. So when this fuel burns, that's the amount of heat that is released as a product. You can take any substance and compare it just like you can compare any mole ratio. 1 mole of fuel releases this much heat. 8 moles of oxygen, 5 moles of carbon dioxide, 6 moles of water. Since the heat is a product, this is an exothermic reaction. You can write the heat in the equation as a product, or you can write it beside the equation with the negative delta H value indicating that heat is released and it is an exothermic reaction. In this reaction, heat is a reactant. This is an endothermic process. If you want to write the energy in the equation, you can write it as a reactant, or you can write it beside the reaction with the positive 250 kilojoules indicating that energy is required or absorbed, and this is an endothermic process. If you want to solve using a thermochemical equation, it's simply a matter of using your stoichiometry and dimensional analysis. How much energy does 5 grams of potassium chlorate absorb? You have all the information above. You can see it's an endothermic reaction that requires 156 kilojoules for every 2 moles of potassium chlorate. So setting up your stoichiometry, you've got 5 grams of potassium chlorate, its molar mass, converting it to moles, and then using the equation where 2 moles are equivalent to 156 kilojoules, and you get the amount of kilojoules absorbed in the reaction of 5 grams of potassium chlorate. This reaction, you also have an endothermic reaction. We want to know how many grams of iron 2 oxide is decomposed if we absorb 2 times 10 to the 5th joules of heat. Again, same concept, set up. This time you're starting with your joules of heat. Using your 3.5 times 10 to the 6 joules is equivalent to 2 moles of iron 2 oxide, and then using the molar mass of iron 2 oxide to get the grams that would require that much heat. Again, all of these problems are very simple stoichiometry. You're simply using your heat and the same method you would use for any mole ratio. If you get a reaction where the heat is written beside, such as this tells you it's an exothermic reaction. This is no different than your previous reactions. It's just a different way of showing you the heat energy associated with that equation. Set your problem up, converting your grams to moles of CH4, and the equation says a mole of CH4 releases 890.3 kilojoules. That's what that delta H at the end of the equation means. Calorimetry is a method in lab that allows us to measure the heat energy that's transferred during a physical or chemical process. The heat energy that's gained or lost is going to be absorbed into water in this instrument called a calorimeter. The heat lost by the reaction will be gained by the water, and we'll then use the water values to calculate that change in heat. In order to measure any amount of heat energy, we must get that heat to be transferred. Remember, heat is the energy that's transferred between two objects at different temperatures. So we need to transfer that heat, and in a calorimeter, we use water because it's able to absorb large amounts of heat energy without changing its temperature to a large degree. So heat lost by the reaction is gained by the water, or heat gained by the reaction is lost by the water. You can tell whether your reaction is endo or exothermic by looking at what happens to the temperature of the water. If the water temperature goes up, it was an exothermic reaction. Heat was lost by the reaction and entered the water. If the water temperature goes down, you can tell it was an endothermic reaction because the water lost heat energy that was gained by the reaction. When you're looking at a change of phase, you notice during the processes of melting and boiling on this graph, you have no change in temperature. Melting and boiling have changes in energy, but it's changes in potential energy, not kinetic energy. So you have no change in temperature when you're going through a phase change. The delta H of fusion and the delta H of vaporization are the heat required to melt and vaporize water. Your heats of fusion, since there's no delta T, you can't use the equation MC delta T. Heats of fusion are releasing or gaining heat, but they're not changing in temperature. All of that heat that's absorbed or released in the reaction is going into breaking or forming those intermolecular forces. None of it is left over to change the motion of the molecules, which is the temperature. So heat of fusion is the energy absorbed to change 1 mole of a liquid from a solid, 1 mole of a substance from a solid to a liquid. So for water, it takes 6.01 kilojoules of heat per mole of water to freeze, or melt it. Calculations are also fairly simple. You'll be given the heat of fusion value. So how much heat energy is needed when you melt 2,000 grams of water? Well, you can't use your equation MC delta T. You're going through a phase change. There is no delta T. So take your 2,000 grams of water, turn it to moles with the molar mass of water, and then use the tabulated or published value of the heat of fusion. 1 mole of water always absorbs that much energy in order to melt. If it was freezing, it would be the same amount of energy, just going in the opposite direction. You would be losing that heat energy in order to freeze. To melt, you're gaining that heat energy. So how much heat energy does it take when you vaporize 2,000 grams of water? Again, 2,000 grams, use the molar mass to convert to moles, and now 1 mole of water requires 40.7 kilojoules. You can see that it takes much more heat energy to vaporize a mole of water than it does to melt it. This is because in the vaporization process, you're breaking all of the hydrogen bonds, while in the melting process, you're only breaking a fraction of those bonds. Heat of vaporization is the energy absorbed when 1 mole of a substance changes from a liquid to a gas. So for water, that value is 40.7 kilojoules per mole. In lab, you will do and find the melting freezing point of a substance by graphing the data. When you reach that flat area, then you know that you're going through a phase change, and you extrapolate back to your temperature, and that gives you the freezing and melting point. Remember, freezing and melting temperatures would be the same. Often, you will find a supercooling situation where you will go below the freezing point and still remain a liquid. And we'll talk about that supercooling phenomenon in class. So for now, this is all that you need to know about heat and most of the heat calculations. And then you will use these heat calculations in your science project when you create your biodiesel fuel and burn it to calculate the amount of energy for each different type of biodiesel fuel.